Let's continue with the last presentation before we end the first day with the panel. Last presentation will be given by Robert Witteck from ISFH, who is part of the Super PV project, and he will stay on the module side and give us an overview on PV module innovations for the reduction of LCOE. Robert, the floor is yours.
Thank you, Michael. So I'll share my screen. Okay, as you mentioned, I will report on the PV module innovations in the Super PV project. And as you can see here from the list of contributors to this part, Super PV is a quite large project with 26 partners in total. And the PV module innovations are developed in work package 3. And here you can see the structure of this work package. We have here on the left-hand side the 6 subtasks we have in this work package. Each task has an innovator or two who develops the innovation and an industrial partner who is going to implement this innovation in his manufacturing or mass manufacturing process. So for 3.1, we have the nano coatings, which are developed by Loredera and Tecnan, and they are implemented by Solitech and Apollon Solar, who are manufacturing PV panels based on crystalline silicon solar cells, and as well by Flisum, who's manufacturing flexible CIGS-based thin film modules. Then we have task 3.2, which is the light harvesting. This is developed by us, by ISFH, and used by industrial partners Apollon Solar and Solitech. The same holds for the in-laminate bypass diode, also developed by ISFH and used by the same partners. In task 3.4, we have the CIGS barrier coating. This one is mainly developed by TNO, and IREC is developing an inline monitoring system for this coating, and this is used by Flisum. So in my talk, I will focus on this 4 work packages, where mainly the main work by the nano coatings and the barriers is provided by TNO, who was so kind to also provide slides for this talk. So I will represent this on behalf of them. We also have the recycling of the modules. So here Syntef and Lux Chemtech are recycling all the modules from Solitech and Apollon Solar and as well as Flisum. And then we have task 3.5, which is mainly performed by the industrial partners who are analyzing the transfer and the costs of the innovation to the mass manufacturing process. So let's start with the nanoparticles, which are developed by Tecnan and Loredera. So they are using a flame spray pyrolysis process to produce their nanoparticles. This is a very versatile technique which allows you to use multi-components, as it can be seen here in this PSE, which highlights the various elements which you can use for this PSE manufacturing process. It allows you to produce nanoparticles with 7 to 25 nanometer size on a very narrow size distribution. And it has the advantage that it has a very short process chain and also comes with a low cost. So, and very a good low cost solution for producing the nanoparticles. After the production of the nanoparticles, they have to be dispersed in a liquid formulation. Here, Loredera and Tecnan decided to go for a formulation which is feasible for the spray gun that you can see here in this image. So this makes it very simple to apply this nano coatings to the PV module in the manufacturing process, either by the spray gun, or you can also apply it maybe in the field, for instance, when you have modules which have no coating on the front side, or in cases nanoparticles are degrading somehow over the years in the field and you want to renew your coating, you can simply apply it also with a spray gun in the field. So this is a very easy application with this spray gun method. Then we here have some results which are first focusing only on this individual single functional nanocoatings. So we have anti-reflective nanocoatings on the one hand side, and on the other side we have this anti-soiling nanocoatings. So for the anti-reflection nanocoatings, Loredera and Tecnan first perform measurements, reflection measurements, shown here as a function of the wavelengths on 2 glasses. One glass shown here in black is a non-treated glass, so without any coating on the front surface. And the red data shows the reflection measurement for glass coated with this anti-reflective coating based on this nanoparticle solution. And you can see that the reflection is reduced by around 20%. And here at the bottom, you can also see the transmission measurements, so the transmittance as a function of the wavelengths. And here you can see again, black data is the non-treated glass, red data is the AR-coated glass. And you can see that this improvement in reflection is not only due to an absorption by the nanoparticles, but also the nanoparticles enhance really the transmittance of the glass. And this eventually will also improve your PV module performance. On the right-hand side, we have nanoparticles that are working as an anti-soiling coating. So here we have two types of nanoparticles, or two effects the nanoparticles can create. One is called HFB. So here we have a hydrophobic anti-soiling coating, and HFL means that we have an hydrophilic anti-soiling coating. And this is best explained in the video here. So here we have a glass. The left-hand side is coated with this HFB coating. So here we have really a repelling effect of the water on the surface. And the right-hand side is coated with this HFL coating. And here we can see that the water starts to wet this entire surface of the glass. So both effects are suitable or possible with this nanocoating solution. And the next step then was in the project to combine both coatings into one multifunctional nanocoating, which then provides the anti-soiling and the anti-reflective properties. So we have here again, not the video, but some images which show you that also this combined multifunctional coating has this anti-soiling properties. And here we have again some measurement, which also shows the reflection is reduced. This one in this case shows the reflection as a function of the wavelengths of the solar cell. So the blue data shows the bare solar cell without any glass. The red data shows the reflection with the untreated glass at the front side. And then we have two possibilities here. We have the gray data showing a single coating at the front side of the glass, which reduces the reflection by about 1.4%. And then we also have the possibility to have multi layer coatings. For here we have a double coating, which further reduces the reflection. And here we have an improvement in reflection or reduction in reflection of 2.8%. And then Luredera also applied this solution to real 60 cell modules provided by Solitech and Apollon. And here they measure a gain of 2% max for the AR and HFB coating, and a slightly lower gain for this of 1% of this AR and HFL coating. And yeah, currently these modules are tested in our outdoor test sites in Super PV. We have 6 outdoor test sites, which will be presented tomorrow by my colleague Julius De Navas. So stay tuned to get results on this tomorrow. Here we have the next work package, which is dealing with the light harvesting. This principle is explained here. We have a solar panel which holds 60 solar cells in blue. And usually we have cell gaps or string gaps between each solar cell. And in a bifacial module, these gaps are transparent. And the innovation here is to put a white reflector on the cell gaps, which is a white color or a white reflector in this case. And this will further improve the light harvesting in the module. And here the first task were to find a suitable printing technique and a suitable color, since there are ceramic colors or organic colors. And then you also have screen printing processes, roller coating processes, or spraying. So we first had to figure out which are the optimal color and printing techniques. And then we performed optical characterization of these colors. And in total, we tested 21 colors, characterized their optics, and tested them in accelerated aging like UV, humidity freeze, and DMP tests. And the next task was to find a suitable geometry that is best explained when you consider such a unit cell of a solar module. So here we have the cell, and this is a gap to the next cell. And here at the bottom, we have the cross section. So here we have our cell, the encapsulant, the front side glass, and the rear side glass. And in a typical bifacial module, light hitting the cell gaps is a large fraction of the light is lost, since it simply transmits through the module. And yeah, with this innovation we have here, we are regaining this light, since we have this reflector in the cell gaps, and this reflector reflects the light in a diffuse manner. And by total internal reflection, we can then regain this light and guide it to the front and rear side of the solar cell. And by this means, we can increase the module power output and the module current. And the challenges here is to find the optical or the optimal geometry of this reflector, since when you make it too small, in the extreme case, you don't have any reflector, so you have a bifacial module. And if you make it too large, you will shade the rear side of the cell, which is then detrimental if you have a ground albedo, where you still want to have this bifacial or bifaciality of the PV modules, so that you can also collect light hitting the PV module from the rear side. So therefore, we used a ray tracing approach, and some results are shown here for a module with a cell gap of 3 millimeters. And this two-dimensional graph here shows the ray tracing simulation results. Here, on the one axis, we have the size of the reflector varying from 1 to 6 millimeter. And here at the bottom axis, we have the ground albedo, which is varying from 0 to 0.7. And the color coding here indicates the gain in short circuit current for a module with a reflector compared to a module which uses only a glass-glass layup, so a simple bifacial module. So when you have a reflector size of 0, we have no reflector, which means that we have a bifacial module. So the gain here is blue, which means that we have a gain of 1. And then when we start increasing the size of the reflector in the simulation, we see that we have a rather steep gradient up to the cell spacing of 3 millimeters. So here's the first broad optimum, you can say, which is very homogeneous for all albedos. And then when you further increase the reflector size, you see that for a very bad albedo, the gain increases. But if you consider an albedo, the gain slightly reduces again, because you simply shade the rear side of your cell in the bifacial module. And then this light is lost because it is absorbed by the absorber. So ideally, if you want to have a module that is applicable for a wide variety of albedo or ground albedos, you want to stay in this region. And then you also have to consider positioning tolerances or manufacturing tolerances of your PV module, which were given here by our industrial partners to be 0.25 millimeters. But in the project, we also figured out that it is very dependent also on the printing technique, since also it very much depends on the manufacturer of your colored glasses. They also have a good variety in the positioning and also the width of your geometry of the white reflector. So in the end, we decided to go for 5 millimeter reflectors in our prototypes. And here we have some results for the prototypes manufactured, in this case by Solitech in a mass manufacturing process. This plot here shows the PMPP, so the maximum power for various modules produced by Solitech. The black data shows the reference. So here we have an average module power of 308 watt. And the red data shows the modules employing this light harvesting innovation. And here we have an average module power of 318 watts. So this gives us an improvement with the light harvesting by about 3%. And when we have a look at the short circuit current, we can also really see here the short circuit current for the same group. So black is again the reference, red is the light harvesting modules. And we can see that this gain really comes from the optical improvement due to the light harvesting in our modules. And also these modules are currently tested on our test sites. Next work package is the in-laminate bypass diode. So the principle is explained here in this figure on the left. So usually you have a module with 60 cells, and per each double string, you usually have a bypass diode, which protects the cells in the double string in case of shading of the PV module. And this close-up here shows how the implementation of the in-laminate bypass diode works. You can simply place or solder this diode in between the two string connector ribbons of each solar string. And that is one advantage. So we also produce this diode with standard PV module or kind of standard PV module manufacturing equipment. So the idea is that a manufacturer can use a pilot line production and use this for producing its own in-laminate or bypass diodes. This is the one advantage, and the other advantage that you can simply replace your junction box. So you don't have a junction box anymore, which is also beneficial for bifacial modules. You have less cabling in the module, and this also reduces the size of the module, which in the end will also improves the efficiency of the module, since you can manufacture slightly. Robert, huh? Thank you. A slightly smaller module. Here we have some pictures. So this is showing the raw diode as it is cut out from the wafer. Here we have the diode soldered in between the cross connector ribbons. And in total, we have produced 300 bypass diodes for Solitech and Apollon, which they use for module integration and that are also currently tested on the demo sites. But we also test them in accelerated aging tests at ISFH. This is shown here. The module power output of one module with this in laminate bypass diode, and we tested in a combined test of humidity freeze and thermal runaways. So this humidity free test is according to the IEC 1215 standard, where you cycle between -40 degrees and 85 degrees and 85% relative humidity. And then we apply also a thermal runaway test, where you apply 1.25 the short circuit current of the module for 1 hour, and then immediately switch after this 1 hour to the diode voltage within 10 milliseconds. And this was mimicking, or this will result in a hot diode, and thermal runaway means that the diode becomes unstable due to this hot condition after 1 hour, and then further runs away and heats up until the diode will be destroyed. And for our test, we have tested now 300 HF cycles and 10 thermal runaway tests, and we haven't seen any degradation of the diodes and only a small degradation of the module, which is less than 2% in this case. The last innovation is the CIGS barrier coating. So the idea here is that usually for a CIGS module, you have a high-grade front sheet, and this is usually very costly, which so this front sheet protects the CIGS and the contact against moisture. And the idea here is to replace this high-grade front sheet, which is costly, with a low-cost front sheet, which is based on PET and coated with an aluminum oxide layer. This is one approach. The other approach would be to directly coat the CIGS layer and then apply this PET layer to the CIGS module. Can be implemented straightforward in this production line by this ALD process, either on the CIGS layer or on the front sheet, and then the backend lamination process. So the aluminum oxide layer here is deposited in an ALD, atomic layer deposition step, which is developed by TNO. They are using this roll-to-roll ALD unit. And here you can see the wheels guiding the PET or the CIGS module in the process chamber. And here we have some results comparing this innovation with the high-grade front sheet. So here we have the normalized efficiency of the module as a function of the damp heat hours. And you can see here that the blue data is showing the reference, the red data is showing the aluminum oxide, and you can see that the degradation is less than 5%. And the conclusion by TNO here is that this aluminum oxide layer on PET gives similar protection as this high-grade front sheet. And then we also have this monitoring provided by IREC for measuring the thickness of this PET or aluminum oxide layer. The measurement is based on reflection. So here we have two approaches, one using LED as a light source. So here we have a light source at 340 and at 660 nanometers. And you can see that the intensity of this peak varies with increasing aluminum oxide layer thickness. And this, from this intensity peak, you can then derive the nominal thickness as a function of a quality factor, which is derived from this measurement, as IREC calls it. And this gives you an idea what is the thickness of your aluminum oxide layer on your PET. The same principle can be applied here, where not using LEDs, but a halogen lamp. So this technique is a little bit more sensitive since you have a broader spectrum for your light source. And here you have a resolution of 2 nanometers. Here you have a resolution of 5 nanometers. But both techniques are suitable for inline monitoring, since you have integration times of less than 100 milliseconds. And that allows you to monitor this thickness of this innovation also in inline manufacturing. And with this, I would like to thank you for your attention and all the partners in the SuperPV project. Thank you.
Thanks, Robert, for this comprehensive overview. I think there are a lot of questions in the chat. We're running a bit late, so I would kindly ask you to address them there.
Sure, I will do that.
Super, thanks. Okay, then let's